Somewhere off the coast of Somalia, in the middle of the ocean, there is a current that does something no current in the Pacific does, and no current in the Atlantic does either. For 6 months it runs north. Then it stops, turns around, and for the next 6 months it runs south. Not gradually, not as a wobble in an otherwise stable flow. It reverses fully, twice every year, on a schedule regular enough that sailors were using it to plan voyages before anyone had a word for oceanography. That alone should sound strange. Ocean currents are supposed to be the stable part of the planet's moving systems. Winds shift by the hour, weather turns on a dime. But currents are driven by the rotation of the Earth, by the shape of ocean basins, by forces that don't change from one season to the next. The Gulf Stream doesn't reverse. The Kuroshio doesn't reverse. The great gyres of the Pacific turn in the same direction in January as they do in July, decade after decade, because the physics that spin them, the Coriolis effect acting on a rotating planet, doesn't take a season off. And yet here, in the northern reaches of the Indian Ocean, an entire current system flips its direction like a tide, except on a calendar of months instead of hours. Ships that once needed to cross the Arabian Sea planned their entire year around it. Sail west in one season, and the water helps you. Try it in the wrong month, and the same stretch of ocean that carried you outbound 6 months earlier will now push you back where you started. This is the case file, the kind built to take a system apart rather than simply marvel at it. What actually flips this current? Why does it happen here, in this one ocean, and nowhere else on the planet at this scale? What did sailors understand about it before scientists did? And where did science initially guess wrong? What does it move besides water? And when oceanographers today say they still don't have the full picture, what exactly is the piece that's missing? We start with the observation, because that's where every real investigation has to start. Not with a theory, with what's actually there. Off the Horn of Africa, roughly between the coast of Somalia and the open Arabian Sea, sits one of the most extreme currents on Earth. During the boreal summer, from roughly June through September, it runs northeast, hugging the coastline, moving with a speed and volume that rivals the Gulf Stream itself, one of the fastest western boundary currents anywhere in the world ocean. Ships that cross it during these months feel the shove. Fishermen who work these waters know to expect cold water rising from below, a cloudy green instead of the usual tropical blue, full of nutrients and full of fish. Then, sometime around October, it starts to slow. By November, it has stalled. By December, it is running the other way, south and west, weaker than its summer self but unmistakably reversed. This pattern repeats every single year. It is not caused by a storm. It is not an anomaly that oceanographers stumbled onto once and have been chasing since. It is the baseline state of this stretch of ocean, and it has been the baseline state for as long as anyone has kept records, and almost certainly for as long as the monsoon winds above it have blown. The first thing worth ruling out is the obvious wrong answer, the one anyone with a passing familiarity with oceans might reach for first. Is this simply a tide? Tides also reverse, after all, twice a day in most places, driven by the gravitational pull of the moon and the sun. But tides operate on a scale of hours, not months, and they reverse the flow of water in and out of a given stretch of coastline, rather than flipping the direction of a current that spans an entire ocean basin. The Somali current's summer surge and winter retreat happen on a completely different clock, tied to a completely different physical driver, and nothing about lunar or solar gravity explains why a current would hold one direction for months and then hold the opposite direction for the next several months. Tides were never a serious candidate here. They're worth naming only because ruling out the wrong answer first is what separates an actual investigation from a guess that happens to sound plausible. To understand why this counts as strange, it helps to look at what every other ocean on Earth does instead. Take the Pacific. Its major currents form what oceanographers call a gyre, an enormous circular system spanning the width of the basin, spinning clockwise in the northern hemisphere and counterclockwise in the southern one. The North Pacific Gyre pulls water up the coast of Asia, across toward North America, down the California coast, and back toward the Philippines, a loop that takes years to complete a full circuit. This loop doesn't stop. It doesn't reverse. The winds that drive its outer edges, the trade winds near the equator and the westerlies further north, blow in consistent directions all year, because they are themselves driven by the planet's basic heat engine. The imbalance between how much sun hits the equator and how much hits the poles. That imbalance doesn't disappear in January. The Atlantic works the same way. The Gulf Stream carries warm water north along the eastern coast of the United States every month of the year, feeding into the North Atlantic Drift that eventually warms the coastlines of northern Europe. Sailors crossing the Atlantic for 500 years have relied on this current running in one direction, because it always does. Christopher Columbus used the trade winds and the currents they drove to reach the Caribbean. Returning ships used a different route further north to catch the Gulf Stream home. Both routes were fixed, neither reversed with the seasons, so somewhere in the mechanics of ocean circulation there is a rule. Currents driven by planetary-scale wind belts. Wind belts locked in place by the rotation of the Earth and the equator-to-pole heat gradient don't change direction. That's the rule that holds almost everywhere. And then there's the northern Indian Ocean, which breaks it cleanly, twice a year, every year. It's worth being precise about what's actually driving those Pacific and Atlantic gyres, because the contrast is what makes the Indian Ocean's behavior so unusual in the first place. Wind blowing across an open ocean drags the surface layer of water with it through simple friction. But the water doesn't just flow in the direction the wind blows. The rotation of the Earth bends moving water to the right in the northern hemisphere and to the left in the southern hemisphere, an effect named for the French scientist who worked out its mathematics, Gaspard Gustave de Coriolis. Wind pushing water gets deflected. That deflected water piles up or drops away from neighboring water. Pressure differences build up in response, and the whole system settles into a balance oceanographers call geostrophic flow, where the pressure gradient and the Coriolis deflection cancel out, and the current settles into a stable path that can persist for as long as the wind driving it holds steady. This is the machinery that locks the Pacific and Atlantic gyres into their permanent clockwise and counterclockwise rotations. It's also, critically, an effect that weakens towards zero as you approach the equator, because the Coriolis effect itself depends on latitude and essentially vanishes at 0 degrees. That detail turns out to matter enormously for this investigation. Close to the equator, in the band running roughly 10 degrees north and south of it, wind-driven water can't settle into the same kind of stable geostrophic balance that holds the mid-latitude gyres in place, because there's not enough Coriolis deflection available to build that balance in the first place. Instead, near-equatorial currents respond much more directly and immediately to whatever the wind is doing at that moment, accelerating and decelerating with comparatively little of the rotational inertia that keeps a mid-latitude gyre spinning in the same direction, even through periods of weaker wind. Keep that fact in reserve. It becomes the explanation for one of the stranger features this investigation runs into further along. Oceanographers also measure the sheer scale of these currents in a unit worth understanding, because it puts the size of the reversal in perspective. Ocean transport is typically measured in a unit called the Sverdrup, each one equal to 1,000,000 cubic meters of water moving past a given point every second, an almost unimaginable volume, roughly equivalent to the combined flow of every river on Earth, passing a single point at once. The The Somali Current at its summer peak carries transport on the order of tens of sverdrups, comparable to the Gulf Stream at its strongest points, which is precisely why comparing this current to the Gulf Stream isn't loose rhetorical flourish. It's an accurate statement about comparable orders of magnitude, two of the most powerful moving masses of water on the planet, one of which happens to reverse itself completely every year and one of which never does. The first explanation anyone reaches for is the simplest one. It's the wind. Ocean currents near the surface are driven substantially by wind stress, the friction of moving air dragging on the water beneath it. If the wind above an ocean basin reverses, it stands to reason the current beneath it might reverse too. And the wind above the northern Indian Ocean does, in fact, reverse. This is the monsoon, and everyone who has spent time in South Asia, East Africa, or the Arabian Peninsula already knows its outline. From roughly June through September, the wind blows from the southwest, carrying moisture off the ocean and dumping it as the rain that agriculture across the Indian subcontinent depends on. From around December through February, the wind reverses, blowing from the northeast, dry and cool, off the Asian landmass and out over the ocean. So far, this checks out. Wind reverses, current reverses, case closed. Except that answer is too easy. And easy answers in a real investigation are usually the ones that collapse the moment you ask a follow-up question. The follow-up question here is obvious. Why does the wind itself reverse so dramatically over this one stretch of ocean? When trade winds over the Pacific and Atlantic hold their direction year-round without any such flip? Wind belts across most of the planet are locked into place by a fairly simple system. Warm air rises at the equator, moves toward the poles at altitude, cools, sinks back down around 30 degrees latitude, and returns toward the equator along the surface, bent by the Earth's rotation into the trade winds. This loop, called a Hadley cell, is remarkably stable. It shifts a little with the seasons, following the sun's position north and south, but it doesn't reverse. The trade winds blow from the northeast in the northern hemisphere tropics essentially all year. The monsoon is a different animal entirely. It isn't a simple piece of the Hadley circulation drifting north and south. It's driven by something much more local and much more violent in its seasonal swing: the enormous landmass of Asia, and specifically the enormous elevated landmass of the Tibetan Plateau, and the Himalayas sitting right in the middle of it. Land and water do not heat up or cool down at the same rate. Water has a high heat capacity, meaning it takes a large amount of energy to change its temperature, and it releases that energy slowly. Land has a low heat capacity by comparison. It heats quickly under the sun and cools quickly once the sun is gone. This difference is the entire engine behind the monsoon. During the boreal summer, the sun sits high over Asia for months at a stretch, and the enormous continental interior heats up fast, faster than the ocean beside it. Hot air rises over the continent, creating an area of low pressure. Meanwhile, the ocean to the south, slower to warm, sits relatively cool, holding an area of comparatively higher pressure. Air flows from high pressure to low, so moist ocean air gets pulled inland, sweeping up from the southwest across the Arabian Sea and the Bay of Bengal, and slamming into the subcontinent, where it's forced upward by mountain ranges and dumps its moisture as monsoon rain. Come winter, the situation flips entirely. The Asian continent, having lost the sun's direct heating, cools rapidly, again faster than the ocean beside it, which is still holding on to summer's stored warmth. Now the continent sits under high pressure, cold and dense air pooling over it, while the ocean holds the relatively lower pressure. Air flows the other way, out from the continent dry and cold, down across the subcontinent and out over the ocean as the northeast monsoon. Call this what it actually is, one of the largest, most violent reversals of atmospheric circulation found anywhere on the planet. a long way past anything a subtle, seasonal drift could produce. The reason it happens here rather than, say, over the middle of the Pacific, comes down largely to geography. Nowhere else on Earth has an ocean basin sitting directly beside a continental landmass of this scale, capped by a plateau high enough to function almost like its own separate climate engine. The Tibetan Plateau averages an elevation higher than most mountain ranges reach at their peaks, and its sheer bulk amplifies the heating and cooling cycle of the land beneath the summer and winter sun, far beyond what a flat continental interior would produce on its own. Some atmospheric scientists describe the plateau as acting almost like a heat pump sitting atop the Asian landmass, intensifying both the summer low and the winter high, well past what simple geography would otherwise generate. There's a specific expression of this wind reversal worth naming directly, because it's the actual physical link between the atmospheric story and the oceanic one. During the height of the southwest monsoon, the wind blowing across the western Arabian Sea doesn't arrive as a diffuse breeze spread evenly across the whole basin. It concentrates into a narrow, extraordinarily fast ribbon of air, low in the atmosphere, that meteorologists call the Findlater jet, named for the researcher who mapped its structure in detail during the 1960s. This jet originates over East Africa, accelerates as it crosses the highlands of Kenya and Somalia, and then rockets out across the open Arabian Sea toward the Indian subcontinent, reaching wind speeds that place it among the strongest low-level atmospheric jets found anywhere on the planet, a title it holds not for a few isolated days but for a sustained stretch of the entire summer monsoon season. This jet matters because it's the direct atmospheric cause of the extreme upwelling off the Somali coast. Wind of this speed and persistence, blowing parallel to a coastline for months, is exactly the ingredient needed to drag surface water offshore, fast enough and consistently enough to pull genuinely deep water up to replace it, rather than the shallower, less nutrient-rich water that weaker or shorter-lived winds would draw up elsewhere. Without the Findlater jet specifically, the Somali coast would still see some seasonal upwelling from the general monsoon pattern, but not upwelling this intense, and not a current surging north at speeds that rival the Gulf Stream. The same wind field also spins up one of the more striking and, for a long stretch of the 20th century, poorly understood features of this entire system, a massive rotating eddy known as the Great Whirl, which forms off the Somali coast every summer as the monsoon current intensifies. The Great Whirl behaves almost like a semi-permanent storm system made of water rather than air, a slowly rotating mass roughly the scale of a small sea, that appears reliably each summer, persists for months, and then breaks down or drifts away as the monsoon winds weaken toward autumn. Its existence puzzled early researchers because it didn't fit cleanly into simple models of wind-driven boundary currents, and it took years of additional current measurements to confirm that it forms through the interaction between the Somali current itself and the coastline it's hugging, an interaction complicated enough that some structural details of exactly how the Great Whirl forms and decays each year are still active subjects of physical oceanography research rather than fully closed questions. Further complicating the picture, though the Great Whirl doesn't sit alone. Research through the latter decades of the 20th century identified a second, smaller rotating feature, sometimes called the Southern Gyre, that forms south of the Great Whirl earlier in the monsoon season and can either merge with it, sit alongside it, or fade out separately depending on the year. A level of year-to-year variability in the eddy field that current models still don't reproduce with complete consistency. Researchers tracking these features by satellite and by direct current measurement have documented cases where the Great Whirl persists in a weakened form well into the winter monsoon season, long after conventional wisdom held that it should have fully dissipated, evidence that the boundary between one monsoon season's current pattern and the next isn't always as clean in practice as the seasonal average makes it look on paper. So the wind reverses because the land beside this particular ocean is unlike any other land beside any other ocean, both in its raw size and in the mountain architecture sitting on top of it. That answers the atmospheric half of the case. It doesn't yet answer the oceanic half, and this is where the investigation has to slow down, because the easy assumption that the ocean current is simply a mirror image of the wind pushing on it turns out to be an oversimplification that the actual data doesn't support. Consider the coastal currents that run along the west and east edges of the Indian subcontinent, the West India Coastal Current and the East India Coastal Current. Both reverse seasonally, much like the open ocean currents further offshore. If the story were purely local wind stress, you'd expect these currents to reverse exactly when the local wind above them reverses. No earlier, no later. That is not what happens. Both coastal currents flip direction at times that don't line up precisely with the local wind shift above them, and the timing mismatch isn't small or explainable as measurement noise. It's consistent, it's been observed across decades of data, and it pointed oceanographers toward a mechanism that has nothing to do with wind blowing directly overhead. The actual driver, worked out through careful analysis over the latter half of the 20th century, involves something called a coastal Kelvin wave. Near the equator, where the influence of the Earth's rotation on moving water essentially vanishes, wind can push up a ridge or trough in sea level that doesn't behave like an ordinary current at all. Instead, it propagates as a wave, trapped against a coastline, traveling along that coast at a speed and in a direction set by the geometry of the basin and the rotation of the planet, carrying the memory of a wind event that happened somewhere else, sometimes weeks earlier and thousands of kilometers away. Here's what that means in practice. When the monsoon winds shift near the equator, close to the coast of Sumatra and the eastern Indian Ocean, they generate a signal that doesn't stay local. It travels, hugging the coastline, moving counterclockwise around the rim of the Bay of Bengal and the Arabian Sea, arriving at the western coast of India not because the wind directly above that coast has changed, but because a wave generated far to the east has finally rounded the corner and arrived. The coastal current along India is carrying a message that started somewhere else, days or weeks ahead of whatever the sky directly overhead happens to be doing that week. This is the first real correction the investigation has to make. It isn't simply that the wind flips and the water dutifully flips with it in lockstep, the same way iron filings snap into line with a magnet the instant the magnet turns. The system carries memory and travels distance. Some of what happens along the Indian coastline in a given month is a direct response to the sky above it that same month, and some of it is an echo of a wind event from further away, arriving late, shaped by the coastline it traveled along the way. Textbook summaries of the monsoon current often collapse this into a single clean sentence: wind reverses, current reverses, and that sentence isn't false, but it hides a genuinely more interesting mechanism underneath it, one where remote forcing and local forcing are tangled together and have to be separated with real data before you can say which is doing how much of the work in any given week. There's a second piece of the system that makes this even clearer, and it involves a discovery that didn't happen until surprisingly late in the 20th century, made by an oceanographer working with old ship logs rather than satellites. In the early 1970s, Klaus Wertke, studying decades of ship drift data collected across the Indian Ocean, noticed something that shouldn't have been there according to the standard picture of monsoon-driven flow. Right along the equator, twice a year. During the narrow transition windows between the two monsoon seasons, a fast eastward jet of water would appear, running along the equator itself, strong enough that ships crossing it noted the drift in their logs even before anyone had formally described the current producing it. These transition windows fall in roughly April and May, as the southwest monsoon is building but hasn't fully established itself, and again in roughly October and November, as the northeast monsoon is building in the same way. During these narrow stretches, The winds along the immediate equatorial band, which for most of the year blow steadily east to west as part of the broader monsoon pattern, briefly relax and can even turn to blow from the west. Because there's essentially no Coriolis effect right on the equator, to redirect that wind stress into a rotating gyre, the water simply accelerates in the direction the wind is briefly pushing it, producing a narrow, fast, short-lived jet running the length of the equatorial Indian Ocean. These are now called the Wirtke jets, and they matter for the case file because they represent a distinct mechanism sitting inside the same overall system. It would be a mistake to describe the Indian Ocean's reversal as one single current flipping on a two-season switch. It's closer to a layered system, a broad monsoon-driven reversal across the whole basin operating on the roughly 6-month rhythm of the wind, a set of coastal currents whose exact timing depends partly on remote wave signals rather than purely local wind, and a pair of brief, fast, essentially separate equatorial jets that appear only in the narrow transition windows between the two main seasons and vanish again within weeks. 3 different mechanisms, tangled into what looks from a distance like a single simple flip. It's worth sitting for a moment on how genuinely surprising these jets were when Wirtke first identified them, because the surprise itself says something about how deeply the simple wind mirrors current assumption had settled into oceanographic thinking by the mid-20th century. Standard models of the era treated the equatorial Indian Ocean as behaving in rough accordance with the prevailing monsoon wind at any given time, flowing broadly westward during the parts of the year when the trade wind component along the equator blew from the east, the way equatorial currents in the Pacific and Atlantic generally do. A fast, narrow, eastward flowing jet appearing twice a year, cutting directly against that expected pattern, didn't fit the existing framework, and it took Wirtke's specific approach, going back through decades of raw ship drift observations, rather than relying on the smoothed, averaged current atlases that had been standard reference tools up to that point, to even notice the signal was there at all. Averaging data across a full season, the standard practice at the time was actually erasing the jets from view, because they only exist for a few weeks at a stretch and get washed out into noise once blended into a broader seasonal average. Finding them required looking at the data on the right timescale, a research choice that seems obvious in hindsight but wasn't the field's default approach before Wirtke demonstrated why it mattered. Not every scientific discovery requires new data. Sometimes it requires asking an old data set a more specific question than anyone had previously bothered to ask it. None of that undermines the wind explanation exactly. The monsoon winds remain the dominant reason this ocean does what no other ocean does. But the investigation reveals that dominant doesn't mean sole, and that the popular version of the story, the one that treats this as a simple mirror between sky and sea, understates how many moving parts are actually stacked underneath it. There's a further detail worth sitting with because it changes how you should picture the whole basin. This dramatic reversal is not something the entire Indian Ocean does. It's confined largely to the northern portion, the Arabian Sea, the Bay of Bengal, and the equatorial band connecting them. South of roughly 10 degrees south latitude, the Indian Ocean behaves much more like the Pacific or Atlantic. A broad, relatively stable subtropical gyre turns there, fed by the south equatorial current, running west across the basin, curling south past Madagascar, and along the African coast as the Agulhas Current, one of the strongest and most studied western boundary currents anywhere on the planet, then swinging east again well south of the equator. This gyre doesn't reverse with the monsoon. It behaves like ocean currents are supposed to behave everywhere else on Earth, locked into a stable rotation by the same Coriolis-driven physics governing the Pacific and Atlantic gyres. The honest picture is an ocean cut into 2 distinct regimes by an accident of geography, and only one of the 2 actually reverses. The southern basin is open, unobstructed by any landmass, free to develop the kind of large, stable, wind and rotation-driven gyre found in every other major ocean basin on the planet. The northern basin is closed off by the bulk of Asia. The Nordostfäden Tenachasciens has no equivalent open expanse to let a stable gyre form, and instead sits directly under the most violent seasonal wind reversal on the planet. So its currents can't help but follow that reversal, instead of settling into the kind of permanent rotation found to its south. This is worth pausing on, because it's the answer to one of the questions sitting at the center of this whole investigation. Why does this happen only in the Indian Ocean and nowhere else at this scale? The explanation traces back to position, not chemistry or seafloor shape. This is the only ocean basin on Earth positioned exactly where a continent large enough and topographically extreme enough to generate a seasonal wind reversal. This powerful happens to sit directly against an ocean basin closed enough in the north that no competing gyre can form to resist it. The Pacific has enormous landmasses on its rim too, but the open Pacific basin is so vast that no single continental heating cycle can flip wind direction across its whole width. The Atlantic's surrounding continents don't reach the scale or elevation of the Asian landmass and the Tibetan Plateau. Only here does the geometry line up, a continent big enough and tall enough to overpower the normal wind pattern, sitting beside an ocean basin boxed in enough in the north to have no alternative circulation to fall back on. The southern, non-reversing half of this ocean has its own share of complexity worth a brief mention, if only to avoid leaving the impression that stable simply means uneventful. The Mozambique Channel, the narrow stretch of water separating Madagascar from the African mainland and feeding into the Agulhas Current described above, doesn't carry a smooth, steady flow the way a simple gyre diagram might suggest. Instead, research using satellite altimetry and current measurements has documented a persistent train of large rotating eddies moving south through the channel, forming with some regularity, drifting along the African coast, and eventually feeding into the Agulhas Current system further south. These eddies influence local fisheries, larval fish dispersal, and regional shipping conditions in the channel, operating on their own semi-regular rhythm distinct from and considerably less predictable in exact timing than the clean seasonal switch driving the northern monsoon system. Even the supposedly stable half of this ocean basin has genuine internal complexity of its own, just of a different character than the dramatic, wind-driven reversal that dominates the north. That's the mechanism, as far as the physical oceanography can currently trace it. Wind reversal driven by extreme land-sea heating contrast, amplified by the Tibetan Plateau, working on an ocean basin closed off in the north by that same landmass, producing a current system with no competing force strong enough to hold a stable direction against it, further complicated by remote wave signals along the coasts and by brief separate equatorial jets during the transition windows. 4 layers, one recognizable pattern from space. The first attempt to explain the monsoon in genuinely scientific terms, rather than as accumulated sailor's knowledge, came far earlier than most people assume. In 1686, the English astronomer Edmund Halley, better known today for the comet that carries his name, published a paper proposing that the monsoon winds were driven by differential heating between land and sea. Essentially the same core mechanism this investigation has spent its opening section establishing, worked out through reasoning rather than instrumentation, using little more than existing ship logs, geographic knowledge, and an understanding of how the sun's heating varies with the seasons. Halley didn't have access to satellite data or upper atmosphere measurements. He had accumulated observations of where and when ships reported favorable and unfavorable winds across the Indian Ocean, and he reasoned his way to a genuinely correct first approximation of the mechanism over a century before anyone had the instruments to test it directly. What's changed since Halley's era isn't whether the basic cause was known. It's how many additional layers of complexity, the Kelvin waves, the equatorial jets, the eddy structure of the Somali Current, have been added underneath that original correct insight. Confirming and refining that insight into the fuller mechanism described so far took nearly 3 more centuries, And a crucial chapter in that confirmation deserves its own mention: the International Indian Ocean Expedition, a large multinational research program that ran through the first half of the 1960s, coordinating research vessels from a number of countries to conduct the most comprehensive systematic survey of Indian Ocean physical, chemical, and biological conditions attempted up to that point. Before this expedition, understanding of Indian Ocean circulation rested heavily on the kind of scattered ship drift data and isolated coastal measurements already described, useful but geographically patchy and inconsistent in timing. The expedition changed that by deploying research vessels to take coordinated, near-simultaneous measurements across wide stretches of the basin, capturing the monsoon transition in a level of systematic detail that hadn't existed before. And the data it produced became foundational to decades of subsequent research, including the ship drift analysis Klaus Wirtke would later draw on to identify the equatorial jets that carry his name. Wirtke himself was directly involved in this broader wave of mid-century Indian Ocean research, and his eventual identification of the jets built directly on the expanded observational baseline this international effort had established less than a decade earlier. The instrumental record kept growing from there. Moored buoys anchored at fixed points began recording temperature, salinity, and current speed continuously through the middle of the 20th century, later expanded by an international observing effort known as the Research Moored Array for African-Asian-Australian Monsoon Analysis and Prediction, a network of buoys strung across the Indian Ocean specifically to give researchers continuous, simultaneous readings from multiple points at once. The Argo program added another layer starting in the early 2000s, deploying thousands of free-drifting robotic floats that sink to a set depth, drift with the current, periodically rise to transmit temperature and salinity readings by satellite, then sink again to repeat the cycle. Satellite altimetry closed the loop from above, measuring the height of the sea surface to a precision of centimeters from orbit to detect the subtle mounding and dipping of water that accompanies major currents and eddies, tracking how those features shift week to week across the entire basin at once. It's the combination of all of these methods, ship logs, moored buoy arrays, drifting floats, and satellite altimetry, cross-checked against each other, that turned the monsoon current system from a pattern sailors trusted by instinct into a mechanism oceanographers can actually describe, measure, and increasingly predict. This work continues today through a handful of institutions that have made Indian Ocean and monsoon research their specific focus rather than a side interest. India's National Institute of Oceanography, headquartered in Goa, runs long-term monitoring programs across the Arabian Sea and Bay of Bengal, contributing much of the regional data that feeds into the broader international picture this investigation has drawn on. The Indian Institute of Tropical Meteorology conducts the modeling and forecasting research behind the monsoon prediction challenges already discussed. Internationally, institutions including the Woods Hole Oceanographic Institution in the United States and Australia's Commonwealth Scientific and Industrial Research Organization have contributed decades of current measurement, buoy deployment, and climate modeling work to the same broader effort, alongside university and government research groups across Japan, the United Kingdom, and the countries bordering the ocean itself. No single institution or country owns this research the way no single civilization ever owned the monsoon trade. It's collaborative in the same practical way the ancient trading network was, because no single vantage point, whether a research vessel, a coastal buoy, or a satellite in orbit, captures the whole system on its own. Before moving from mechanism to consequence, the investigation owes itself two more rule-outs, because both are common enough misconceptions to be worth addressing directly rather than leaving as loose threads. The first is river runoff. Given how much fresh water pours into the Bay of Bengal from the Ganges and Brahmaputra river systems, it's a reasonable guess that seasonal flooding from these rivers might be what drives the current reversal on that side of the subcontinent rather than wind. The data doesn't support this as the primary driver, though it isn't irrelevant either. River discharge does measurably affect salinity and stratification in the Bay of Bengal, which is part of why that side of the subcontinent behaves differently. As this investigation gets to shortly, but the actual reversal of current direction tracks the monsoon wind cycle far more closely than it tracks river discharge timing, and the same reversal happens on the Arabian Sea side of the subcontinent, where no comparable river system exists at all. If river runoff were the primary driver, the Arabian Sea current shouldn't reverse the same way the Bay of Bengal current does. It does reverse on essentially the same schedule, which rules river discharge out as anything more than a secondary regional modifier layered on top of the wind-driven mechanism. The second is the relationship to El Niño, worth separating clearly from the Indian Ocean dipole discussed later in this investigation. El Niño is a real, well-documented influence on monsoon strength, and weak monsoon years do correlate with El Niño conditions in the Pacific with reasonable statistical consistency. But El Niño is not the mechanism causing the current to reverse in the first place. The reversal happens every single year, in El Niño years, in La Niña years, and in years with neither pattern present, because it's driven by the land-sea heating cycle described earlier, a cycle tied to the Earth's orbit around the Sun, and therefore essentially guaranteed to repeat every year regardless of what the Pacific is doing. El Niño and La Niña modulate how strong or weak a given monsoon season turns out to be. They don't switch the reversal on or off. And that distinction between a system's basic mechanism and the outside influences that make any single year of it stronger or weaker than average is worth keeping in mind for what comes later in this investigation as well. It's worth running a brief thought experiment to make the geographic argument fully concrete. Because counterfactuals are often the clearest way to test whether a proposed mechanism actually explains what it claims to. Imagine the Asian landmass were removed from the map entirely, replaced by open ocean extending north from the equator, the way the Pacific and Atlantic both do. Under that scenario, there would be no extreme continental heating and cooling cycle to drive a seasonal wind reversal in the first place. And the trade winds across this hypothetical open northern Indian Ocean would very likely settle into the same kind of stable, Coriolis-balanced pattern found across the equivalent latitudes of the Pacific and Atlantic. A stable wind pattern would drive a stable gyre, and the whole reversing current system this investigation opened with would simply not exist. Run the thought experiment the other direction. Imagine the Tibetan Plateau were absent, the Asian landmass present but flat, and at low elevation like most other continental interiors. The land-sea heating contrast would still exist, because land and water still have different heat capacities regardless of elevation, but it would be considerably weaker, closer to the gentler West African monsoon discussed later in this investigation than to the extreme system actually observed here. Both halves of this thought experiment point to the same conclusion the evidence has already supported. Remove either ingredient, the closed northern basin, or the extreme elevated landmass beside it, and the reversal weakens or disappears. Both ingredients present together, in this one specific configuration, is what produces the system as it actually exists. Human history only covers the most recent sliver of this system's existence, and it's worth asking how far back the monsoon itself actually goes, because the answer reframes everything on a considerably longer timescale. Paleoclimate researchers, working from sediment cores drilled from the seafloor of the Arabian Sea and the South China Sea, have reconstructed a monsoon history stretching back tens of millions of years, tied directly to the geological uplift of the Tibetan Plateau itself. As the Indian tectonic plate collided with Asia and pushed the plateau upward, a process that began roughly 50 million years ago and continued over tens of millions of years afterward, the growing elevation progressively intensified the land-sea heating contrast this investigation has identified as the monsoon's core driver, strengthening the seasonal wind reversal as the plateau grew taller. Sediment records show corresponding shifts in dust deposition, oceanic productivity, and the chemical signatures upwelling leaves behind, evidence that the Somali Current's summer upwelling and the broader monsoon current system aren't a recent or incidental feature of this ocean, but a consequence that has been building, in step with the mountains themselves, for longer than most of the planet's current ocean basins have held their present shape. The version of the monsoon that ancient sailors read 1,000 years ago and the version an oceanographer measures today are, in this light, a comparatively recent snapshot of a system that has been intensifying for tens of millions of years, and, on the geological evidence available, is still doing so. But a mechanism explains how the water moves. It doesn't yet explain what people did with that knowledge, and the answer to that turns out to be one of the oldest continuously used pieces of environmental knowledge in human history. Long before anyone had a theory of Hadley cells or coastal Kelvin waves, sailors along the rim of this ocean had worked out the practical consequence of the monsoon system through pure observation, repeated across generations, until it became embedded in how entire economies operated. Arab and Persian traders were sailing dhows across the Arabian Sea to the western coast of India for centuries before anyone wrote the pattern down formally. The rhythm was simple in practice, even if the underlying physics wasn't understood. Leave the Arabian Peninsula riding the southwest monsoon, when both the wind and the current push you east and north toward India. Conduct trade, wait out the season, then return riding the northeast monsoon months later, when wind and current both reverse and carry you home. Getting the timing wrong didn't just mean an uncomfortable voyage. It could mean being stranded on the wrong coast for half a year, waiting for the pattern to flip back, or fighting headwinds and countercurrents the entire way, burning through provisions with no guarantee of making landfall before running out. Swahili traders along the East African coast, from Somalia down through Kenya, Tanzania, and beyond, built an entire commercial civilization around this same rhythm, exchanging goods with Arabia, Persia, and India across the width of the ocean, their port cities rising and falling in coordination with a wind pattern most of their merchants couldn't have explained in atmospheric terms, but every one of them could read like a calendar. Swahili coast communities, who arguably had more continuous direct experience with this wind system than any other culture along the ocean's rim, developed their own vocabulary for it independent of the Arabic and later European terms that ended up dominating the written historical record. The Swahili language names the two monsoon winds Kaskazi, the dry northeast monsoon blowing down from Arabia and driving trade south toward East Africa, and Kusi, the wetter southwest monsoon that reverses the pattern and carries trade back north, terms still in everyday use along the Kenyan and Tanzanian coast today, embedded in place names, poetry, and the practical vocabulary of contemporary fishing and sailing communities whose working lives still track these same two winds. The traditional sailing vessel most associated with this trade, the dhow, actually describes a broad family of related hull and rigging designs rather than a single standardized boat, ranging from smaller coastal vessels to larger ocean-going ships capable of carrying substantial cargo across the open crossing to India, typically built with a distinctive triangular lateen sail well suited to the kind of sustained, predictable wind. This investigation has spent considerable effort explaining the physical origin of dhow construction techniques passed down through boat-building communities along the Arabian and East African coasts for centuries, were themselves an engineering response to the specific wind and sea conditions this system generates. Further evidence of how completely this one wind and current pattern shaped not just when people sailed, but what kind of vessel they built to do it in. The earliest surviving written account that lays this system out in detail for outsiders is the Periplus of the Erythraean Sea, a Greek merchant's handbook composed in roughly the 1st century of the Common Era, describing ports, goods, and crucially the timing of monsoon-driven voyages across what the author called the Erythraean Sea, the ancient term covering the Arabian Sea, and the waters beyond it toward India. The document reads less like literature and more like a working shipping manual, because that's exactly what it was. Written by someone who needed sailors to actually arrive where they were going, rather than drift for months on a badly timed crossing. Roman and Greek historical tradition credits a navigator named Hippolus with discovering the direct open ocean route across the Arabian Sea, sailing straight across using the monsoon wind, rather than hugging the coastline the long way around, through the Persian Gulf and down the Arabian coast. Pliny the Elder records the story a few generations later, treating it as a genuine breakthrough in Roman trade with India. But treat that story with the same scrutiny the rest of this case deserves. Because the claim that a single Greek sailor discovered this route doesn't hold up well against everything else in the historical record. Arab, Persian, and Indian mariners had almost certainly been making direct monsoon crossings for a very long time before any Greek or Roman ship attempted it, simply because they lived on both sides of the route and had every reason to work out the shortest crossing, long before Mediterranean traders showed any interest in reaching India directly. What Hippalus most likely did, if the story has any basis at all, was learn a route that local sailors already knew and bring that knowledge into Roman shipping networks, which is a very different achievement than discovering it outright, and a very familiar pattern in how credit for practical knowledge tends to get reassigned in written history to whoever first wrote it down in a language that later scholars kept reading. The monsoon trade network stretches back further than any of the written sources so far mentioned, deep enough into prehistory that the documentary record thins out into archaeology instead. Excavations at Lothal, a Bronze Age port site in present-day Gujarat associated with the Indus Valley Civilization, have revealed what many archaeologists interpret as a dockyard structure dating back roughly 4,000 years, evidence of a maritime trading culture exchanging goods with Mesopotamia across the same general stretch of ocean that Arab dhows and Portuguese caravels would later cross using the identical seasonal wind pattern. Nobody in that era left behind an explanation of monsoon mechanics, but a functioning port built to handle seasonal maritime trade implies a working knowledge of when ships could reliably come and go. Knowledge that had to have been monsoon-timed even if no surviving text says so directly. Centuries later, the Chola dynasty of southern India built one of the more striking naval powers of the medieval Indian Ocean world, launching documented overseas expeditions across the Bay of Bengal into Southeast Asia during the early second millennium, projecting political and commercial influence toward the Srivijaya Empire centered on Sumatra, an empire that itself grew wealthy largely by controlling the strait through which monsoon-timed shipping between India, China, and the wider archipelago had to pass. Srivijaya's entire strategic position depended on sitting astride a monsoon choke point, collecting tolls and trade revenue from ships that had no practical alternative route if they wanted to catch the seasonal winds connecting the Indian Ocean to the South China Sea. Control of a stretch of water this narrow positioned exactly where monsoon-timed traffic had to funnel through was worth more to a medieval Southeast Asian kingdom than control of a comparable stretch of open ocean would ever have been, precisely because the monsoon calendar left shipping with so little flexibility in when and where it could pass. This is worth naming plainly. Long before any European ship entered these waters, the northern Indian Ocean rim hosted a rotating cast of major trading powers: Harappan port cities, Arab and Persian merchant fleets, Swahili city-states, Chola naval expeditions, Srivijayan choke point control, each built, in some fashion, around the same seasonal wind and current system this investigation has been tracing from its physical origins. The monsoon wasn't a backdrop these civilizations happened to operate within. It was closer to shared infrastructure, an unowned, unbuilt transportation system that every power along its rim had to learn to use on its own terms, because none of them had the ability to change its schedule. The monsoon trade network these mariners built connected an extraordinary range of ports across an enormous stretch of ocean, from the Red Sea and the Persian Gulf, along the Arabian Peninsula, down the East African coast, across to the western coast of India, around the southern tip of the subcontinent, and up into the Bay of Bengal towards Southeast Asia. Goods moved through this network in volumes that rival anything the more famous Overland Silk Road ever carried. Spices, textiles, ivory, gold, timber, ceramics, and eventually people in both the ordinary sense of travelers and merchants and in the far darker sense of the slave trade that also moved along these same monsoon-timed routes. None of it moved on a schedule set by ports or by rulers. It moved on a schedule set by wind and current. 6 months one direction, 6 months the other. A rhythm indifferent to whoever happened to be in charge of any given port in any given century. The word monsoon itself carries a trace of this history. It comes from the Arabic mausim, meaning season, by way of Portuguese and Dutch traders, who picked up the term from Arab pilots and merchants they worked alongside in Indian Ocean ports and carried it back into European languages. That a word borrowed from Arabic became the standard international scientific term for this wind system is a small but telling detail, an acknowledgement, even if an unintentional one, of whose knowledge the concept actually originated from. Arab navigators didn't just know when to sail. They built a genuine navigational science around it, using a star compass system that divided the horizon into fixed points, marked by the rising and setting positions of specific stars, allowing a pilot to hold a course through open ocean at night with real precision long before European ships in this region had anything comparable. The most famous name associated with this tradition is Ahmad ibn Majid, a 15th century Arab navigator and author of detailed sailing manuals covering monsoon timing, star navigation, and the geography of Indian Ocean ports, whose writing is sometimes cited in connection with Vasco da Gama's crossing, though the exact nature of that connection remains debated among historians. What isn't in dispute is that Ibn Majid represents a written tradition of accumulated, systematized monsoon knowledge that existed in the Arab world well before European navigators arrived, seeking exactly that knowledge for themselves. By the early 15th century, this same rhythm was carrying the largest wooden ships the world had ever built. The Chinese Admiral Zheng He led a series of enormous naval expeditions out from China, down through Southeast Asia, across the Indian Ocean to India, the Arabian Peninsula, and the East African coast, commanding fleets that dwarfed anything Europe would put to sea for another century. Historical Chinese records describe individual voyages involving several hundred ships and crews numbering in the tens of thousands, sailing together across a route that depended entirely on getting the monsoon calendar right at every leg. These voyages weren't improvised. Fleet departures and return legs were planned around the same monsoon calendar that Arab dhow traders had been reading for 1,000 years already, because there was no getting around it. Ships that size, dependent on wind for the bulk of their propulsion, simply couldn't fight a reversed monsoon current and a reversed monsoon wind at the same time across open ocean, not reliably, not without losses that no fleet commander could accept. When European ships finally arrived in this ocean at the very end of the 15th century, they arrived as newcomers to a trading and navigation system that was already extraordinarily mature. Vasco da Gama's fleet reached the Indian port of Calicut in the year often written as 1498, and the crossing that got him there from the East African coast to India was made with the help of local navigational knowledge, most commonly identified in historical accounts as coming from an Arab or Gujarati pilot familiar with the monsoon-timed route, a detail that later Portuguese chroniclers weren't always eager to emphasize, for obvious reasons. Da Gama didn't discover a new ocean route so much as he was guided across an old one. The same monsoon rhythm that had carried traders across this water for well over 1,000 years before his ships arrived. What followed was a rapid European effort to master the same calendar the Arab, Persian, Swahili, Indian, and Chinese traders had been reading for centuries. The Portuguese crown, and later the Dutch and English trading companies that displaced Portuguese dominance in the region, built their entire Asian trade operations around monsoon timing. The Dutch East India Company and its English counterpart both organized what were effectively annual monsoon fleets, ships that had to depart Europe by a certain window in order to round the southern tip of Africa, catch the trade winds and currents up the East African coast, and arrive in the Arabian Sea or the Bay of Bengal in time to ride the correct monsoon into Indian or Southeast Asian ports. Miss the window and a ship might spend an extra season anchored somewhere along the route, an enormously expensive delay when a ship's entire commercial value depended on completing round trips as quickly as the wind pattern allowed. The economic stakes behind getting this timing right were enormous. A single successful monsoon-timed voyage to the Spice Islands and back could return profits to Dutch or English investors, many times the original cost of outfitting the ship, driven by the price gap between what pepper, cloves, nutmeg, and cinnamon cost at their point of origin and what they sold for once they reached European markets. The Dutch East India Company went so far as to enforce a violent monopoly over clove and nutmeg production in specific island groups in the East Indies, destroying trees outside its controlled territory to keep supply and therefore price under its control, a policy that only worked because the company could reliably schedule fleets to collect and ship the harvest, using the monsoon-timed route year after year. None of that commercial architecture, the monopoly enforcement, the annual fleet scheduling, the investment cycles that early trading companies pioneered, would have been possible without a predictable current and wind system to build the calendar around. The monsoon wasn't incidental to this history. It was the clock the entire enterprise ran on. British East India Company records from the 17th and 18th centuries reveal just how rigidly monsoon timing structured commercial life across an entire trading empire. Ships bound for India and beyond were expected to clear English ports within specific windows, tied to the broader Atlantic and Indian Ocean wind systems. Arriving in Indian waters in time to catch the correct monsoon leg for onward trade, before turning around to catch the reverse monsoon home, a round trip that, when timed correctly, could be completed within a single annual cycle, and when timed incorrectly, could strand a ship and its cargo for the better part of a year, waiting for the pattern to realign. This rigid scheduling gave rise to what traders of the era called the country trade, a network of regional voyages conducted by company-licensed private merchants operating within Asian waters between monsoon seasons, filling the gaps left by the company's own long-haul ships. The marine insurance industry that grew up around this trade, centered in London and closely associated with the Lloyd's coffee house market that would eventually become Lloyd's of London, priced risk directly around monsoon predictability. A voyage undertaken within the expected seasonal window carried one risk profile. A voyage that departed late, or that attempted to run against the monsoon current and wind rather than with it, carried a measurably higher risk of loss, delay, or damage, and underwriters of the period adjusted their rates accordingly, effectively pricing the physical oceanography of the Indian Ocean into the earliest institutions of modern maritime insurance, decades before anyone could have explained why the pattern they were pricing around behaved the way it did. It's worth reconstructing briefly what all of this actually meant for someone living inside the system rather than studying it centuries later. A merchant captain working the Arabian Sea trade 1,000 years ago would have planned an entire year's income around a calendar, shaped by everything this investigation has now traced back to its physical origins. Departure from a port on the Arabian coast would come in early summer, time to catch the building southwest monsoon, wind and current both pushing the vessel east and north across open water toward the Indian coast. A crossing that, favorably timed, could take a matter of weeks rather than the months a poorly timed or coast-hugging route might require. The captain couldn't simply turn around and sail home once trade was finished. The wind and current that carried the ship east were still blowing the same direction, and attempting to sail directly back against both would have been slow at best and genuinely dangerous at worst. So the ship and its crew and its cargo waited. Months passed in port. Trade continued. Relationships were built with local merchants who would matter again next season, until the calendar turned and the northeast monsoon established itself, wind and current now reversed, ready to carry the same ship home along a route that 6 months earlier would have fought it every mile of the way. This wasn't an inconvenience captains grumbled about. It was simply how the ocean worked, absorbed so completely into commercial life across this entire region that entire economic systems, port city growth cycles, harvest and market timing on both sides of the crossing, all synchronized to the same underlying wind and current mechanism now described in physical terms. The risk of getting it wrong was never purely theoretical either. Maritime archaeologists have recovered wrecks scattered across this ocean's trade routes, from Arab dhows to Portuguese carracks to Dutch East Indiamen. And while shipwrecks have many causes, storms, navigational error, poor construction, a meaningful share of the losses recorded in period accounts and insurance records trace back to vessels that misjudged the monsoon calendar, departing too late in a season, lingering too long in a port, or attempting a crossing. During the unstable transition weeks, this investigation is already identified as the most dangerous window on the calendar. The ocean didn't forgive a miscalculation just because the miscalculation was honest. It applied the same physics to every ship that entered it, regardless of flag, cargo, or how badly the voyage needed to succeed. The monsoon's reach extended well beyond commerce and into the cultural fabric of the societies living under it, a dimension worth naming, even briefly. Across South Asia, the arrival of the southwest monsoon is marked by festivals, poetry, and popular art built around the specific sensory experience of the rains breaking after months of dry heat, a cultural weight that reflects just how central this single seasonal event is to daily life across the subcontinent. Classical and folk traditions across India have long treated the monsoon's arrival as a subject worth songs and verse in its own right, an acknowledgement expressed through culture, rather than instrumentation, of the same dependency. This investigation has spent considerable length describing in physical and economic terms. Picture the physical experience of that reversal from the deck of a vessel crossing it, because the abstractions of wind belts and Coriolis deflection can obscure just how directly sailors felt this system operating on their bodies. A ship running with the southwest monsoon in July doesn't drift gently along a current. It gets pushed, sail straining, hull cutting a visible wake against water that's moving almost as fast as the wind driving it, the two forces working together rather than one merely following the other. Sailors crossing against the grain of that same current in the wrong month described exactly the opposite sensation. A ship that seemed to fight for every mile, sails full and straining yet making barely perceptible progress against a mass of water surging the other direction beneath the hull. Provisions dwindling, while the coastline that should have been receding stayed stubbornly in view. That visceral, physical difference, current and wind either compounding each other or canceling out whatever progress a ship's rigging could otherwise generate, is what turned monsoon timing from an abstract calendar note into a matter sailors felt in their arms, hauling on lines, and in the food stores they watched shrink day by day. The physics this investigation has spent so much effort describing in terms of pressure gradients and heat capacity was, for every person who ever crossed this water before satellite forecasting existed, something closer to a fact of the body than a fact of the atmosphere. This is worth sitting with for a moment because it reframes the entire European age of exploration narrative that tends to dominate popular history of this ocean. European ships weren't conquering an unpredictable wilderness through superior seamanship. They were slotting themselves into a transportation system that had been engineered, in the practical sense, by generations of Arab, Persian, Indian, Swahili, and Chinese navigators who had already solved the hard problem of when to sail and when to wait. The monsoon current didn't care whose flag was on the ship. It rewarded whoever had bothered to learn its schedule and punished whoever hadn't, regardless of how advanced their navigation instruments were. Even as steam power and later diesel engines freed shipping from total dependence on wind, the monsoon current system didn't stop mattering. It simply changed how it mattered. A modern container ship doesn't need the wind to move it forward, but it still burns considerably more fuel fighting a strong opposing current than it does riding a favorable one. And across an ocean where a major current reverses by a meaningful fraction of a knot to several knots, depending on location and season, that difference adds up over the length of a major shipping route. Fuel efficiency planning for ransom vessels crossing the Arabian Sea and the wider northern Indian Ocean still accounts for the seasonal current pattern, even if it's now treated as a variable to be optimized around rather than a hard constraint that determines whether the voyage is possible at all. The opening of the Suez Canal in the latter half of the 19th century changed the geography of this trade permanently, cutting out the long voyage around the southern tip of Africa and with it, the Agulhas current leg of the old monsoon-era route. But it didn't remove the monsoon system from the calculation entirely. Ships still had to cross the Arabian Sea and, depending on their onward destination, the Bay of Bengal, still subject to the same seasonal current and cyclone risk this investigation has already traced, just without the extended African detour that had shaped shipping schedules for the previous 4 centuries. Modern commercial shipping now relies on weather routing software that ingests real-time current, wind, and wave data, including the same satellite altimetry and buoy network measurements described earlier, to calculate fuel-optimal paths across ocean basins, including this one, a computerized, continuously updated descendant of the same seasonal planning that Arab pilots and East India Company captains once carried in memory and in handwritten sailing manuals. The underlying physical reality being optimized around hasn't changed. Only the tools doing the optimizing have. The Indian Ocean's monsoon-shaped geography also carries continuing strategic weight in modern naval planning. The United States operates a significant naval and logistics base on the atoll of Diego Garcia, positioned well south of the most extreme monsoon reversal zone but still within the wider basin this investigation has covered. Chosen in part for its position along sea lanes that global shipping, still shaped by the currents and choke points traced from ancient trade routes onward, continues to depend on. 2 narrow choke points bookend this ocean's monsoon zone, and both carry outsized weight in modern energy and shipping markets precisely because so much of the traffic passing through them is still shaped by the seasonal wind and current patterns this investigation has traced back to their physical origins. The Strait of Hormuz, at the mouth of the Persian Gulf, sees a substantial share of the world's seaborne oil exports pass through a channel narrow enough that a handful of shipping lanes carry effectively all of it, and vessels transiting that strait to reach Asian or European markets still cross the Arabian Sea on a route where the monsoon current and cyclone season remain genuine operational factors. Further south, the Bab el-Mandeb Strait, connecting the Red Sea to the Gulf of Aden and the wider Arabian Sea, sits at the historic gateway between the Mediterranean world and the monsoon trading system. This investigation has spent considerable length describing a choke point that Arab, Ottoman, and later European powers all recognized as strategically decisive for exactly the same reason ancient traders did. Control this narrow gap, and you control access to everything the monsoon calendar makes possible on the other side of it. The monsoon also still governs a much more dangerous seasonal hazard for modern shipping: tropical cyclones. Both the Arabian Sea and the Bay of Bengal generate cyclones primarily in the narrow transition windows before and after the 2 monsoon seasons. The same weeks when the Wirtke jets appear along the equator, when atmospheric conditions are shifting from one stable pattern to the other, and instability spikes as a result. Shipping routes, insurance calculations, and port operations across the region all build around avoiding these transition windows in vulnerable areas, a modern echo of the same seasonal caution that shaped monsoon fleet departures 500 years ago. Just translated into satellite forecasts and marine insurance premiums instead of accumulated sailors' lore. These transition window cyclones aren't a hypothetical risk. Cyclone Ganu, which formed in the Arabian Sea in June of 2007, grew into the strongest tropical cyclone ever reliably recorded in that basin, making landfall in Oman and causing damage and loss of life across the Arabian Peninsula. A stark illustration of how much energy can accumulate in these waters during the exact weeks when the monsoon system is shifting from one seasonal state to the other. On the other side of the subcontinent, the Bay of Bengal has an even longer documented history of catastrophic transition window cyclones, including the 1999 Odisha cyclone, one of the most powerful storms ever recorded to strike the Indian coastline, which caused mass casualties and remains a reference point for disaster preparedness planning across the region today. Both storms formed in the narrow atmospheric window this investigation has already identified as unusually unstable, and both are treated by meteorologists and disaster planners as evidence that this transition period deserves exactly the kind of caution modern forecasting now devotes to it. The monsoon still shapes activity on these waters in ways that have nothing to do with cargo or fish. Piracy off the coast of Somalia, a serious and well-documented problem for international shipping through the 2000s and into the following decade, showed a measurable seasonal pattern tied directly to the same wind and sea state conditions this investigation has been tracing. Pirate attacks using small, open skiffs launched from the Somali coast dropped sharply during the peak months of the southwest monsoon, when the Findlater jet whips up sea conditions too rough for small boats to operate safely far from shore, and picked back up during the calmer transition and northeast monsoon periods when the sea state allowed skiffs to range much further from the coastline in relative safety. International naval task forces patrolling the region through this period built their operational planning around exactly this seasonal rhythm, treating the monsoon calendar as a genuine tactical variable, because the same wind system that once dictated when merchant dhows could safely cross this stretch of ocean turned out to dictate centuries later, when small pirate skiffs could safely do the same thing. So the current doesn't just move water. It moved economies for over 1,000 years, shaped which civilizations along this ocean's rim grew rich and which stayed marginal, decided which European power could realistically compete for Asian trade and which couldn't, and it still shapes fuel costs and cyclone risk for the shipping that keeps a significant share of global trade moving today. That's the human half of the case file. The other half, the ecological half, turns out to be just as tightly wound into the same mechanism. Start with the Somali coast again, because that's where the reversal is most extreme, and where its ecological consequences are most visible. During the southwest monsoon, as the current surges north along the Somali coastline, it doesn't just move surface water, it pulls water. The wind blowing parallel to the coast, combined with the Coriolis effect, drags surface water away from the shore, and deeper water rises up to replace it, a process oceanographers call coastal upwelling. That deep water is cold, and far more importantly, it's loaded with nutrients that have been sinking out of the sunlit surface layer for months. Nitrogen and phosphorus compounds that phytoplankton need to grow, and that are otherwise scarce in the nutrient-poor surface waters typical of tropical oceans. When that nutrient-rich deep water reaches the sunlit surface, phytoplankton bloom explosively. This is the base of an entire food web, springing to life on a seasonal clock. Zooplankton graze the phytoplankton bloom. Small fish graze the zooplankton. Larger fish, including commercially critical species like tuna, follow the small fish. Seabirds and marine mammals follow the fish. For a few months every year, the waters off Somalia and the southern Arabian Peninsula turn into some of the richest feeding water found anywhere in the open ocean, a seasonal pulse of life triggered directly by the same current reversal that carried merchant dhows north 1,000 years earlier. This upwelling has a darker companion, though, one that reveals just how tightly the biology and chemistry of this ocean are locked to the monsoon cycle. All that surface productivity eventually dies and sinks, and as it decomposes, It consumes oxygen. In most oceans, this process is diluted enough, and mixing with oxygen-rich water is thorough enough that it doesn't create major problems. In the Arabian Sea, it does. The Arabian Sea hosts an oxygen minimum zone among the most intense measured anywhere on Earth, and unusually, among the shallowest, a layer of water at intermediate depth so depleted of dissolved oxygen that most fish and larger marine animals simply can't survive there. This zone owes its existence directly to the same monsoon-driven productivity that makes the surface waters so rich. The system essentially manufactures its own low-oxygen graveyard as a byproduct of the very fertility the monsoon current creates. That oxygen minimum zone isn't a static curiosity either. It hosts unusual microbial chemistry, including significant production of nitrous oxide, a potent greenhouse gas, through bacterial processes that thrive specifically in low oxygen conditions. In water this starved of oxygen, certain microbial communities switch to using dissolved nitrogen compounds instead of oxygen to break down organic material, a process called denitrification that converts biologically available nitrogen back into forms that escape into the atmosphere. And the Arabian Sea is recognized as one of only a small number of locations on the planet where this process runs at a scale significant enough to matter for the global nitrogen budget, alongside a comparable zone in the eastern tropical Pacific. In other words, the same seasonal reversal that built ancient trading empires also runs a chemical process with global climate and nutrient cycling implications, quietly, at depth, every year. Tied to a schedule set by wind direction over a continent thousands of kilometers inland. The Bay of Bengal, on the other side of the Indian subcontinent, tells a genuinely different story despite sitting under the same overall monsoon system, and the contrast is instructive. Rather than strong upwelling, the Bay of Bengal receives an enormous seasonal flood of fresh water from major rivers, principally the Ganges and the Brahmaputra, draining meltwater and monsoon rainfall off the Himalayan watershed. This fresh water sits on top of the denser, saltier ocean water beneath it, creating a strong layer of stratification that actually suppresses the kind of vertical mixing that drives upwelling on the Arabian seaside. The result is a bay that, despite sitting under the identical wind reversal driving the Arabian Sea's productivity, behaves quite differently in terms of nutrient cycling and biological productivity, less driven by upwelling, more shaped by riverborne nutrients and the stratification the freshwater layer imposes. There's a specific piece of this physics worth naming precisely, because it deepens the freshwater stratification point rather than just restating it. The layer of fresher water sitting atop the saltier water below in the Bay of Bengal creates what oceanographers call a barrier layer, a stable buffer zone that limits how effectively storms and wind can mix cooler, deeper water up to the surface, which in turn allows surface temperatures in the bay to stay unusually warm through much of the year. This warm surface layer connects to a larger feature spanning the eastern Indian Ocean and the western Pacific, known as the Indo-Pacific Warm Pool, one of the warmest expanses of open ocean surface water on the planet, and a significant source of energy and moisture for the entire regional atmospheric circulation, including the monsoon system this investigation has been tracing. The barrier layer's presence is part of why the Bay of Bengal, despite receiving the same overall monsoon wind forcing as the Arabian Sea, tends to produce more intense, rapidly strengthening cyclones. Warm surface water resists being cooled and disrupted by the storm's own churning in a way that would otherwise weaken the system, because the barrier layer keeps the storm's energy source insulated from the cooler water just beneath it. This is a genuinely different physical mechanism from the wind-driven current reversal at the center of this investigation, but it shares the same root cause: the seasonal fresh water delivery tied to monsoon rainfall and Himalayan runoff. This matters for the investigation because it's a check against oversimplifying the whole system into a single, clean mechanism. The same monsoon wind reversal produces two markedly different oceanic responses on the two sides of the same subcontinent, because local geography, in this case the presence of enormous river systems draining into one side and their relative absence on the other, changes how the wind's energy actually plays out in the water. The mechanism is consistent. The consequences are not, and a full accounting of this system has to hold both of those facts at once, rather than collapsing everything into one tidy summary. Marine life across the wider basin has adapted its migratory and reproductive timing to this rhythm over evolutionary timescales, not just human ones. Tuna and other large pelagic fish track the upwelling zones as they intensify and fade with the monsoon cycle, and fisheries across the region from Somalia and Yemen through Oman and down the Indian coastline have historically timed their fishing seasons to the same current pattern that ancient traders timed their voyages to. Where the current brings food, fish congregate, and where fish congregate, fishing fleets follow. A chain of dependency running from wind to current, to nutrient, to plankton, to fish, to the economies of coastal communities that have relied on this cycle for as long as anyone has fished these waters. The seasonal upwelling doesn't only feed commercial fisheries, it draws some of the ocean's largest animals into a predictable, documented seasonal aggregation. Whale sharks, the largest fish in the ocean, gather in significant numbers off the Arabian Peninsula, particularly in the Gulf of Oman and nearby waters, during the period when monsoon-driven upwelling concentrates plankton dense enough to make filter feeding worthwhile for an animal that size. And researchers tracking these aggregations have tied their timing directly to the same current and upwelling cycle, driving the rest of the region's productivity. Coral reefs across the northern Indian Ocean live a more complicated relationship with this same cycle. The cooler water that upwelling brings to the surface during the southwest monsoon can offer some relief to reefs during the hottest part of the year, a natural buffering effect against the kind of heat stress that triggers coral bleaching elsewhere in warming tropical oceans. But the same monsoon season also brings increased wave energy, sediment runoff, and lower salinity in areas affected by heavy freshwater input, all of which carry their own separate stress on reef systems. So the net effect isn't simply protective. It's a trade-off that varies significantly by location. That trade-off became starkly visible during two well-documented mass bleaching events in 1998 and again in 2016, both years when a strong El Niño in the Pacific coincided with unusually warm conditions across large sections of the Indian Ocean. Reef surveys conducted across locations including the Chagos Archipelago, the Seychelles, and parts of the western Indian Ocean recorded severe coral mortality during both events, with some individual reef systems losing the majority of their live coral cover within a matter of months, as sustained above-average temperatures overwhelmed whatever buffering effect the upwelling might otherwise have provided in a typical year. Researchers studying these events have specifically examined the interaction between El Niño conditions in the Pacific and the state of the Indian Ocean dipole, discussed shortly during the same years, finding that the two systems reinforcing each other, rather than counteracting each other, appears to correlate with the most severe basin-wide bleaching outcomes. When they align, the consequences compound rather than simply add. Mangrove forests along the coastlines of the Arabian Sea and Bay of Bengal depend on the seasonal rhythm of freshwater delivery that the monsoon provides, timing seed dispersal and growth cycles to the rains. Sea turtles nesting along beaches on both sides of the subcontinent likewise show nesting seasons that correlate with the monsoon calendar, though the relationship there runs more through rainfall and beach temperature than through the ocean current directly. Across all of these systems, the through line is the same. A huge share of the biological calendar of this ocean is set not by day length or a fixed annual clock, the way it might be at higher latitudes, but by the arrival and departure of a wind-driven current system that most of these species have no way of sensing directly, only its consequences. There's a more recent, more troubling ecological wrinkle connected to this same upwelling system, documented by researchers including Joaquim Goes and Helga do Rosario Gomes, studying Arabian Sea plankton communities over the past 2 decades. Since roughly the turn of the millennium, the winter monsoon bloom in the northern Arabian Sea has shown a marked shift away from the diatom-dominated phytoplankton communities that historically supported the region's fisheries, toward blooms increasingly dominated by an organism called Noctiluca scintillans, a bioluminescent single-celled organism that, unlike diatoms, sits closer to the bottom of the food web usefulness scale for fish and other higher predators, offering considerably less nutritional value to the food chain that depends on it. Published research connects this shift to warming surface waters and changes in oxygen conditions tied to the same monsoon-driven upwelling and stratification system already described, suggesting that a warming climate may be altering not just the timing or strength of the physical current system, but the biological outcome of the productivity it generates. This remains an area of active research rather than a fully resolved finding, but it's a concrete published example of how the layered uncertainty this investigation returns to in its closing section isn't a purely academic question. It already has a measurable foothold in the base of the region's marine food web. The monsoon's influence on regional fisheries has become formal government policy in several countries along this ocean's rim, a modern regulatory echo of the same seasonal rhythm ancient fleets once navigated by instinct. India enforces an annual fishing moratorium along significant stretches of its coastline, timed to coincide with the peak of the southwest monsoon, a period when rough seas make fishing more dangerous and when many commercially important fish species are spawning. Owindo Regional Fisheries Authorities have determined offers fish stocks their best chance to reproduce successfully before the fishing fleet returns to the water once the monsoon eases. Similar seasonal fishing restrictions exist across other countries along the Arabian Sea and Bay of Bengal coastlines, each essentially formalizing, through fisheries management law, what fishing communities in this region have understood through direct experience for generations. Millions of people across the coastal communities of this ocean's northern rim derive their livelihood, directly or indirectly, from fisheries tied to this seasonal cycle, which means the monsoon current's economic reach today extends well beyond shipping and into the daily working lives of a very large regional population, most of whom will never think about Coriolis deflection or coastal Kelvin waves, but every one of whom times critical parts of their working year around the same underlying mechanism this investigation has spent its length trying to make explicit. There's a wider atmospheric connection to draw out here as well, because the monsoon current doesn't operate in isolation from the rest of the planet's climate system. And this is where the investigation has to zoom out from the Indian Ocean itself to the broader machinery it's plugged into. The monsoon rainfall that this wind and current system delivers to South Asia isn't a minor regional weather event. It's one of the largest single sources of fresh water for agriculture on the planet, supporting food production for well over 1 billion people across India, Pakistan, Bangladesh, and neighboring countries. A weak monsoon year, one where the rains arrive late, deliver less total rainfall, or include long, unexpected dry spells in the middle of the season, translates directly into reduced crop yields, water shortages, and in severe cases genuine humanitarian consequences across a huge and densely populated region. A monsoon that arrives too strong, on the other hand, brings flooding capable of displacing millions of people and destroying the same crops a weak monsoon would have starved. The system has to land somewhere close to its historical average, and it usually does, but usually is doing a lot of work in that sentence because the exceptions have real human costs. To make the scale of what's actually moving through this system concrete, consider the water budget involved. The southwest monsoon delivers the overwhelming majority of India's annual rainfall within the span of roughly 4 months. A concentration of precipitation Almost nowhere else on the planet experiences at this scale relative to its population and agricultural dependency. Reservoirs, groundwater recharge, and the planting calendar for staple crops across the subcontinent are all built around the assumption that this 4-month window will deliver close to its historical average, an assumption that, when it holds, supports one of the largest concentrations of agricultural production and population on Earth, and when it fails by even a modest margin, can trigger water stress across hundreds of millions of people within a single growing season. Very few weather systems on the planet carry consequences at this scale, attached to a single seasonal average, holding roughly steady year after year, which is part of why so much scientific and governmental attention gets devoted to understanding a system whose basic mechanism was already worked out by sailors who never had the vocabulary of atmospheric physics to describe what they were relying on. Discovering exactly what nudges the monsoon toward a stronger or weaker year turned out to be one of the more genuinely surprising research threads to come out of Indian Ocean oceanography in recent decades. For a long time, monsoon variability was studied mostly by looking east, toward the Pacific, because the El Niño Southern Oscillation, the well-known cycle of warming and cooling across the tropical Pacific, was already known to influence weather patterns across much of the world, including South Asia. El Niño years do tend to correlate with weaker Indian monsoons, and La Niña years with stronger ones, a connection oceanographers had documented reasonably well by the latter part of the 20th century. But in the late 1990s, a separate pattern was identified sitting entirely within the Indian Ocean itself, independent of what the Pacific was doing. Researchers, including Nagoya-based oceanographer Toshio Yamagata, and colleagues described a mode of variability in which the western Indian Ocean, roughly the area off the East African coast, and the eastern Indian Ocean, roughly the area near Sumatra and Indonesia, would periodically develop a temperature difference between them, one side running warmer than usual, while the other ran cooler, then relaxing back, then sometimes flipping to the opposite configuration. This came to be called the Indian Ocean Dipole, and it wasn't simply a passive readout of Pacific conditions bleeding across a connected ocean system. It behaved as its own coupled ocean-atmosphere phenomenon, with its own feedback loop between sea surface temperature and wind, capable of developing independently of what was happening in the Pacific, though the two systems do interact and can either reinforce or counteract each other in a given year. This was, in its own way, a second necessary correction for the investigation, because the prevailing assumption before the dipole was well described treated Indian Ocean climate variability as essentially downstream of the Pacific, a regional ripple off a bigger, better understood global pattern. It is not simply a smaller echo of El Niño playing out in a different ocean. It is its own engine, with its own feedback mechanism between warming water, shifting wind, and further warming or cooling water, capable of driving significant swings in East African rainfall, Australian bushfire risk, and Indonesian drought conditions on a schedule that doesn't always line up with the Pacific cycle at all. A positive phase of the dipole, warmer water in the west, cooler in the east, tends to bring devastating drought to Indonesia and Australia, while simultaneously driving heavy, sometimes catastrophic flooding rainfall across East Africa. A negative phase tends to do roughly the opposite. And because this dipole interacts with the monsoon system, sometimes amplifying it, sometimes working against it, understanding one system properly now requires tracking the other alongside it, a level of interconnection that oceanographers only really began mapping out with any confidence within the last 3 decades. The most recent clear demonstration of the dipole's independent power came in 2019, when the Indian Ocean swung into one of the strongest positive dipole events on record, western waters running unusually warm, eastern waters unusually cool. East Africa endured extraordinary flooding rainfall through the following months, displacing large numbers of people across Kenya, Somalia, and Ethiopia, while at the same time, on the other side of the basin, Australia moved into what became one of its most severe bushfire seasons in modern record-keeping, conditions widely linked by climate researchers to the drying influence of that same dipole event suppressing rainfall across the Australian continent. Two catastrophic, seemingly unrelated events, a flood on one side of an ocean and a fire season on the other, traced back to the same coupled temperature swing playing out simultaneously at both ends of the same basin. There's a related trend worth flagging in the same breath, because it connects the cyclone risk described earlier to this broader climate discussion. Historically, the Arabian Sea produced meaningfully fewer tropical cyclones than the Bay of Bengal, a long-recognized asymmetry attributed to differences in sea surface temperature, wind shear, and the overall structure of monsoon circulation on the two sides of the subcontinent. Published research over the past decade, including work associated with oceanographer Roxy Matthew Cole and colleagues at the Indian Institute of Tropical Meteorology, has documented a measurable rise in the frequency and intensity of Arabian Sea cyclones in recent decades, alongside the faster-than-average warming trend already noted for the wider Indian Ocean basin. Cyclone Ganu sits within this broader pattern of an ocean basin that appears to be growing more capable of generating storms of a severity it rarely produced in earlier instrumental records. Whether this represents an early, clearly attributable signal of long-term climate change, or whether it falls within a wider range of natural decadal variability that simply hadn't been captured yet in the shorter instrumental record available before satellite monitoring became reliable, is treated cautiously in the published literature itself, with researchers generally describing a documented trend while stopping short of definitive long-term attribution. Which brings the case file to its final section, the part where a real investigation has to be honest about where the trail runs cold, at least for now. The basic mechanism behind the seasonal current reversal is genuinely well understood, and none of what follows should be read as undermining that. Land-sea heating contrast, amplified by the Tibetan Plateau, drives a wind reversal of a scale unmatched anywhere else on Earth. And that wind reversal, working on an ocean basin closed off in the north, drives the current reversal, with coastal Kelvin waves and equatorial jets adding real but secondary complexity on top of the core pattern. That much has been tested, confirmed, and refined across decades of ship data, buoy networks, and satellite observation. This isn't a phenomenon anyone credible still calls a mystery in the sense of not knowing what causes it. What remains genuinely unresolved sits one level up, in the precision of prediction rather than the existence of mechanism. Forecasting exactly when the monsoon will arrive in a given year, down to the specific week, remains stubbornly difficult, even with modern satellite data and enormously more sophisticated climate models than existed even 20 years ago. The monsoon doesn't just arrive or fail to arrive as a single event either. Within a single season, it commonly includes what meteorologists call active and break periods, stretches of heavy, consistent rainfall interrupted by stretches where the rain nearly stops entirely for a week or more before resuming, and predicting exactly when these breaks will occur, how long they'll last, and how severely they'll affect any particular region remains one of the harder open problems in seasonal weather forecasting anywhere in the world. Pin down what unresolved actually means in practice by looking at one specific, concrete forecasting problem meteorologists in the region face every single year, predicting the onset date of the southwest monsoon over the Indian state of Kerala, the traditional marker used to declare the start of the season across the whole subcontinent. The India Meteorological Department issues an official onset forecast months in advance, and then a more refined forecast closer to the date, using a combination of wind, rainfall, and outgoing radiation criteria built up over decades of observation. Even with all of that accumulated data and modern computing power behind it, onset forecasts routinely carry an uncertainty window measured in days to weeks rather than hours, and years still occur where the actual onset arrives well outside the range the forecast confidently predicted. Part of the difficulty traces back to an atmospheric pattern separate from anything discussed so far in this investigation, a slower, roughly 30 to 60-day oscillation in tropical rainfall and wind known as the Madden-Julian Oscillation, first described by Roland Madden and Paul Julian in the 1970s while studying tropical Pacific data, which turns out to modulate monsoon onset timing and the strength of active and break periods within a season in ways that are still being incorporated into operational forecasting models. Global coupled climate models, the same large-scale simulations used for long-term climate projections, have historically struggled specifically with reproducing Indian Ocean and monsoon dynamics accurately, a limitation acknowledged openly within the climate modeling community itself, where models that perform reasonably well simulating other parts of the global climate system still show systematic biases when it comes to the timing, strength, and internal variability of this particular wind and current system. None of this means the mechanism is in doubt. It means predicting the exact behavior of a mechanism this well understood, at the resolution scientists and the people depending on the forecast would like, remains genuinely hard. And saying so honestly is different from saying the underlying system is mysterious. There's also a longer-term question that current research hasn't fully settled. What is actually happening to the strength of this system as the planet warms? The Indian Ocean has been warming at a rate that a number of published studies over the past decade have found to be faster than the global ocean average, a genuinely striking finding given how large this basin is. In principle, faster ocean warming should intensify the land-sea temperature contrast that drives the monsoon in the first place, potentially strengthening it. But the picture on the ground is more tangled than that simple logic suggests, because South Asia has also seen a dramatic rise over the same period in atmospheric aerosols, the fine particulate pollution produced by industrial activity, vehicle emissions, and biomass burning across the region, sometimes referred to collectively as the Asian brown cloud. These aerosols can reflect incoming sunlight before it ever reaches the surface, partially offsetting the warming that would otherwise intensify the land-sea contrast. And different regional studies analyzing decades of rainfall records have reached somewhat different conclusions about whether the net effect over recent decades has been a strengthening monsoon, a weakening one, or one that's held roughly steady in total rainfall while becoming more erratic in its internal timing and distribution. Recent published research has continued to refine and in some cases complicate this picture. Studies analyzing satellite and in-situ temperature records into the 2020s have generally confirmed that Indian Ocean warming is proceeding at a pace that outstrips the global ocean average. With some regional analyses attributing a meaningful share of this to the basin's unique geography, an enclosed northern end that traps heat less effectively into deep circulation compared with oceans that have open connections at both poles. Separate research has also examined how the Pacific Decadal Oscillation, a slower, multi-decade pattern of Pacific temperature variability distinct from the shorter El Niño cycle, interacts with Indian Ocean conditions and, by extension, monsoon strength, adding yet another layer of multi-decade variability that has to be statistically separated from any underlying warming trend before a confident long-term conclusion can be drawn. Researchers working on these questions have been explicit in published discussions that disentangling a genuine forced warming trend from this stack of overlapping natural oscillations, the Pacific Decadal Oscillation, El Niño and La Niña, the Indian Ocean Dipole, and whatever multi-decade internal variability the monsoon system itself carries independent of all three, remains a substantial statistical and modeling challenge, one that additional decades of continuous satellite and buoy data collection will be needed to resolve with real confidence. This is, again, not a gap in knowing the mechanism. It is the ordinary, unglamorous difficulty of separating signal from noise in a system with this many overlapping natural rhythms layered on top of each other. The most recent major international climate assessment, compiled by the Intergovernmental Panel on Climate Change and released in stages through the early 2020s, addressed the South Asian monsoon specifically within its regional projections, and its conclusions track closely with the layered uncertainty already described here. The assessment projects with moderate to high confidence depending on the specific metric that mean monsoon rainfall is likely to increase somewhat over the coming decades as the planet continues to warm. Driven by the added moisture a warmer atmosphere can hold, while simultaneously projecting increased year-to-year variability and a higher likelihood of extreme rainfall events clustered into shorter, more intense bursts. It also explicitly flags continuing low confidence in projections of monsoon onset timing and the frequency of active and break periods within a season, precisely the fine-grained predictability questions already identified as the genuine open edge of the science. Reading a document like this alongside everything traced so far confirms the shape of the case rather than complicating it further. International climate science, working from an entirely different angle and an entirely different set of models than the historical and oceanographic evidence assembled throughout this investigation, arrives at the same basic split. Confident about the mechanism and its general direction, considerably less confident about the precise year-to-year and week-to-week behavior riding on top of it. That last possibility, a monsoon that delivers roughly the same total rainfall over a season, but distributes it far less evenly, arriving in fewer, more intense bursts rather than steady, consistent rain across the whole season, appears with some consistency across multiple independent studies of Indian rainfall records over recent decades. And it may turn out to be the more accurate way to describe what's actually changing rather than a simple, stronger or weaker framing. But this remains an active area of published disagreement among researchers working with overlapping but not identical data sets and modeling approaches, and it would be dishonest to present it here as a settled question with a single clean answer, when the actual state of the published science is still a genuine, ongoing argument. Layered on top of that is the question of whether extreme phases of the Indian Ocean dipole, the kind capable of triggering severe drought in Australia and Indonesia alongside catastrophic flooding in East Africa, are becoming more frequent as the ocean warms. Several recent studies point in that direction, and the East African flooding and Horn of Africa drought events of the past several years have renewed scientific and public attention on the dipole's behavior. But attributing any single event cleanly to a long-term warming trend, as opposed to natural year-to-year variability that this system has always displayed, even without any additional warming pushing on it, requires statistical care that the field is still actively working through, and researchers publishing in this space are generally careful to describe trends rather than certainties. So here's where the trail actually stands, stated plainly rather than dressed up as either solved or unsolved. The mechanism causing the reversal itself is not in serious scientific dispute. What remains genuinely open is the fine-grained predictability of that mechanism from year to year, and the longer-term trajectory of the whole system under a warming climate, where multiple competing physical effects, ocean warming pushing one direction, aerosol pollution pushing another, dipole variability adding its own independent swing on top of both, are still being untangled from decades of imperfect and sometimes conflicting data. That is not a failure of the science. It's an honest description of a system with enough moving parts that pinning every one of them down precisely every year in advance may simply be a harder problem than pinning down the underlying mechanism ever was. Step back one more time before closing this file, because it's worth being precise about the shape of what's been resolved and what hasn't, rather than letting the two blur together the way casual summaries of this system tend to. Resolved. The reversal exists. It's driven by a wind system with a clearly identified physical cause rooted in continental heating contrast that wind system's extremity traces to a specific, identifiable geographic combination found nowhere else on the planet. The ocean's response involves at least three distinguishable mechanisms working at different scales and timings, and centuries of accumulated human navigation, trade, and now instrumental science have each independently confirmed the pattern from a different angle. Sailors' logs, moored buoys, drifting floats, and orbiting satellites all telling the same underlying story, unresolved genuinely and currently. The exact week a given year's monsoon will arrive, how long its internal brakes will run, whether its total strength is trending up, down, or simply becoming less evenly distributed under a warming climate, how reliably the Indian Ocean dipole's most extreme phases will recur as that warming continues, and how a handful of overlapping multi-decade natural cycles can be cleanly separated from a longer-term forced trend using an instrumental record that, in satellite terms, only really begins in the latter part of the 20th century. That's not a small list of open questions, but it's also not the same kind of gap that would let anyone reasonably call this system mysterious, in the way that phrase usually gets used as a stand-in for not knowing. The mechanism is known. The precision at the edges of that mechanism is what remains under active investigation. And drawing that line clearly is the entire point of taking a case like this apart, rather than simply marveling at it from a distance. Zoom out far enough, and this ocean stops looking like an isolated case and starts looking like one node in a much larger planetary pattern. The Indian monsoon isn't the only monsoon system on Earth. West Africa has its own monsoon, driven by a similar, if less extreme, land-sea heating contrast across a different continent. East Asia has a monsoon system of its own, interacting with but distinct from the Indian system, shaped by its own continental geography and its own version of the same underlying physics. Even parts of North America and northern Australia experience monsoon-like seasonal wind and rainfall reversals, weaker and less studied than the Indian case, but built from recognizably the same ingredients. Look specifically at how these other regional monsoons compare, because the differences are as instructive as the similarities. The West African monsoon operates on a broadly similar land-sea heating principle, driving seasonal rainfall across the Sahel region south of the Sahara. But the temperature contrast driving it is considerably gentler than the contrast generated by the Asian landmass and the Tibetan Plateau, and correspondingly, West Africa's monsoon-driven ocean currents in the adjacent Atlantic never approach the scale or totality of reversal seen in the Somali current. Sahel rainfall variability tied to this weaker monsoon system has nonetheless carried enormous consequences of its own, including documented multi-decade drought periods through the latter 20th century that reshaped agriculture and migration patterns across the region. A reminder that even a comparatively modest monsoon system, by Indian Ocean standards, can still dictate the fate of tens of millions of people. The East Asian monsoon, affecting China, Korea, and Japan, is driven by a related but distinct configuration of the same underlying land-sea contrast, complicated further by the specific track of a rain band researchers call the Meiyu Front in China and the Baiyu Front in Japan, which advances and retreats across the region in a pattern connected to, but not identical to, the timing of the Indian monsoon further west. The two systems interact meaningfully, sometimes reinforcing each other's timing and sometimes not, part of a larger web of Asian monsoon subsystems that atmospheric scientists increasingly treat as a connected whole rather than a set of independent regional weather patterns. Northern Australia experiences its own monsoon, driven by the same basic seasonal reversal of continental heating relative to the surrounding ocean, though on a landmass far smaller than Asia and without anything resembling the Tibetan Plateau to amplify the effect, producing a monsoon season that's real and consequential for the region's ecology and indigenous seasonal calendars, but nowhere near the scale of atmospheric and oceanic disruption the Indian system generates. Line all of these systems up side by side, and a clear pattern emerges. The size of the reversal scales closely with the size and elevation of the landmass driving it, and no other landmass on Earth combines the raw scale of Asia with the elevation of the Tibetan Plateau sitting on top of an ocean basin closed off the way the northern Indian Ocean is. What makes the Indian Ocean version the most dramatic expression of this pattern on the planet comes back to the same geographic accident this investigation kept circling back to. Nowhere else does a landmass this large, capped by a plateau this extreme, sit directly beside an ocean basin closed off enough in the north to let the wind's reversal fully take over the water beneath it, uncontested by any stable competing gyre. Every other monsoon system on Earth is a quieter cousin of this one, built from the same physics, working at a smaller scale, because nowhere else does geography stack the ingredients quite this dramatically. There's one more connection worth tracing before closing this file, because it links the calmer, more conventional southern half of this ocean back into a planetary system every bit as consequential as the monsoon itself. The Agulhas Current, the stable, non-reversing western boundary current that runs down the African coast, south of the monsoon-affected zone, doesn't simply complete its loop and rejoin the South Indian Ocean gyre, the way a textbook diagram might suggest. As it reaches the southern tip of Africa, a portion of its warm, salty water breaks away from the main current in the form of enormous rotating rings, sometimes called Agulhas rings, that detach and drift west into the South Atlantic, carrying Indian Ocean heat and salt across an entire ocean boundary into a different basin altogether. This leakage, as oceanographers call it, feeds directly into the Atlantic meridional overturning circulation, the deep global conveyor system that redistributes heat between the tropics and the North Atlantic, and plays a documented role in regulating climate as far away as Western Europe. Some published research has proposed that Agulhas leakage may act as a stabilizing influence on that overturning circulation, though the precise strength of that influence and how it might change as the climate continues to warm remains an active subject of ongoing study rather than a settled number. It's a fitting closing thread for this investigation. The same ocean whose northern half runs on a wind-driven switch unlike anywhere else on Earth has a southern half quietly leaking its water into the machinery that helps regulate climate on the far side of the planet, a reminder that no single ocean basin, however strange its local behavior, is ever really operating in isolation from the rest of the system it's embedded in. That's the case, laid out as plainly as the evidence allows. An apparent anomaly that turned out, on inspection, to be something else entirely. A fully mechanistic system, driven by an extreme accident of continental geography, working on the one ocean basin positioned to let that accident dictate its currents, rather than the planet's usual rotational rules. A system that ancient sailors read accurately for over 1,000 years before science caught up with an explanation for what they'd already learned to trust. A system that still governs fuel costs and cyclone risk for modern shipping, still manufactures both a seasonal feast and an oxygen-starved graveyard in the same stretch of water, and still holds enough genuine unpredictability at its edges, in the timing of its arrival, the strength of its brakes, and its long-term trajectory under a warming planet, that oceanographers studying it today are honest about not having the last word. Somewhere off the Somali coast right now, depending on which month you're watching this, the current is either building toward its summer surge north or settling into its quieter winter drift south. Either way, it's running on the same schedule it's run for as long as anyone has been able to check, precise enough that people built empires around trusting it, uncertain enough at its finer edges that people are still building careers around studying it. If there's another ocean anomaly you want a case file built around next, something you've heard mentioned once and never fully explained, put it in the comments below. That's usually where the next investigation actually starts. alike does the unglamorous work of pushing a mechanism like this one in front of people who'd never have gone looking for it, which is most of the reason anyone ends up understanding a current they'd never heard of an hour earlier. And if tracing a system down to what's really driving it is the kind of thing you want more of, subscribing is the easiest way to make sure the next case file finds you when it's ready.